Elon talks about 1 million people on Mars by 2050. Sounds impossible until you break down the real problem. Each person needs 10 tons of supplies yearly. That's 10 million tons total, every single year. Launching that from Earth with rockets? The fuel costs alone make it completely unrealistic. So SpaceX is building something on the moon that launches cargo without any fuel at all. Sounds crazy, right? But the physics actually works. So Mars is sitting out there, roughly 225 million kilometers away at the closest point. Everything a colonist needs has to travel that entire distance. We're talking food, water, tools, spare parts, medical supplies, all of it. Starship can haul about 100 tons to Mars per trip, which honestly seems impressive until you start doing the math. A colony of just 1,000 people needs somewhere around 10,000 tons of supplies every year just to stay alive. That means 100 Starship launches annually for a relatively small settlement. Now scale that up to Elon's 1 million-person vision, and the numbers get completely absurd. What really gets me is the fuel situation. Each Starship burns through 3,400 tons of propellant just getting off the ground. If you're running those 100 supply missions we talked about, you're consuming 340,000 tons of methane and oxygen per year. Think about that for a second. You'd need an entire industrial complex on Earth dedicated solely to producing rocket fuel for Mars logistics. The launch costs alone, even at SpaceX's most optimistic projections of $10 million per flight, would run into the hundreds of billions annually. There's simply no way this works long-term if everything keeps launching from Earth. Which brings us to the moon, and this is where I think the broader strategy starts making sense. Most people see the moon as this intermediate step, like we're going there to practice before the real Mars missions begin. But that completely misses the point. The moon isn't practice, it's infrastructure. It's the key piece that makes the entire Mars plan economically viable. Look at the basics. Lunar gravity is 1/6 of Earth's, which means you need roughly 36 times less energy to reach escape velocity. There's no atmosphere either, so you skip all the aerodynamic heating and drag that complicates every Earth launch. But what really matters are the resources sitting right there on the surface. Those permanently shadowed craters near the poles contain water ice. You can split that into hydrogen and oxygen for propellant. The regolith has silicon for solar panels, various metals for construction, materials you can process into building components. In theory, once you get mining and refining operations running, the moon becomes largely self-sufficient for bulk materials. The catch is rockets still don't solve the fundamental problem, even on the moon. Yeah, lunar gravity is lower, but you're still building expendable launch vehicles over and over. Each one needs engines, fuel tanks, guidance systems, all the complex hardware that makes rockets expensive. You save on fuel, but the operational costs keep stacking up. That's what makes the mass driver concept so compelling to me. And I know it sounds like something out of a sci-fi novel, but the physics has been solid since the 1970s when researchers first tested small-scale versions. The basic idea is pretty straightforward. You build a track lined with electromagnetic coils and place your cargo in a carrier that's basically just a metal container. No engines, no fuel, no complex systems. When you activate the launcher, electrical current flows through the coils in sequence, creating magnetic fields that accelerate the carrier forward. Each coil fires precisely as the carrier approaches, then shuts off after it passes. The acceleration builds smoothly until you hit lunar escape velocity, about 2.4 kilometers per second. Then the carrier releases, and you're off to wherever you're aiming. What strikes me about this system is how well it matches the moon's conditions. You can generate electricity using solar panels, and near the poles you get sunlight 80 to 90% of the time, based on NASA's mapping data. Set up your solar arrays, add some capacitor banks for energy storage, and you've got a launch system that runs on pure electricity. No propellant production, no cryogenic storage, no refueling between launches. Now, the acceleration forces are absolutely brutal. Hundreds or thousands of Gs. You couldn't put a human anywhere near this thing, and most electronics would get crushed instantly. But raw materials, refined metals, processed water ice, none of that cares about G-forces. You can subject basic cargo to extreme acceleration without any degradation. The design that makes the most sense uses a circular track inside a crater. Instead of building one long straight accelerator, the carrier loops around multiple times, picking up speed with each pass. A 500-meter diameter circle gives you effectively several kilometers of acceleration distance as the payload goes around and around. Plus, the crater walls provide structural support, which cuts down massively on how much construction material you need to bring from Earth. The whole thing runs on magnetic levitation too, so there's no friction, no wear on the track surface. When I look at the capacity numbers from those 1980s studies, that's when this really clicks for me. They estimated a full-scale mass driver could move 100,000 to 600,000 tons per year. Those aren't wild projections. They're based on reasonable operational schedules and maintenance windows. Compare that to current global launch capacity, which is maybe 1,500 tons annually across every rocket worldwide. A single lunar mass driver would outperform Earth's entire space industry by a factor of 100 or more. The operational rhythm is completely different too. Rockets need days or weeks between flights for inspections and refurbishment. A mass driver. You're limited mainly by cargo loading time and how fast your capacitors recharge. You could potentially launch multiple times per day, every day, as long as you have payloads ready to go. Power requirements are significant but not crazy. Moving 100,000 tons per year needs continuous power equivalent to a small town, roughly 10 to 20 megawatts. The launch bursts themselves need much higher instantaneous power, which is why the energy storage becomes critical. But solar works remarkably well on the Moon. No atmospheric absorption, continuous tracking near the poles, consistent output. What really sells me on the economics is comparing this to a traditional rocket operation on the Moon. Building the mass driver probably costs a few $100 million, maybe up to $1 billion, depending on specifications. That sounds like a lot until you realize 5 Starship launches cost about the same. After you build it, your ongoing expenses are basically maintenance and electricity. Meanwhile, a rocket-based system needs constant propellant production, cryogenic facilities, launch pad maintenance, engine refurbishment. The costs never stop accumulating. With a mass driver, you pay up front and then run it for decades. So what's actually happening right now? SpaceX isn't putting out press releases about mass driver development, but you can trace the progression if you pay attention. They're committed to this 2028 timeline for lunar landing. Trump's executive directive turned it into a national priority. NASA's paying nearly $3 billion for the Starship lunar lander work, and the political pressure is real. 3 years might sound like plenty of time, but for space development it's incredibly tight. Ship 39 and Booster 19 are currently going through prep for Flight 12. Ship 39 had a rough go earlier this year. A high-pressure gas system failed during ground testing and destroyed an earlier vehicle completely. They've since replaced multiple gas tanks and reworked the plumbing specifically to prevent that kind of failure again. The testing process is methodical. Cryo-proof testing to verify tank integrity, thrust simulation to check structural loads, Raptor installation, then finally static fire before flight clearance. What matters for the bigger picture is that every Starship test proves out systems needed for lunar operations. The in-space refueling tests are particularly critical because you can't do a long-duration moon mission without multiple tanker launches. Ship-to-ship propellant transfer at this scale has never been attempted, and getting it reliable is absolutely essential. But here's what gets me thinking about mass drivers, Starship's cargo capacity. A single flight can deliver 100 tons to the lunar surface. That's enough for major components of an electromagnetic launcher. The coils, power electronics, solar panels, construction robots. 10 flights puts 1,000 tons of hardware on the moon, which is enough to bootstrap serious industrial infrastructure. The timeline isn't impossible if you think it through. 2028 gets astronauts on the surface, probably just a short-duration mission. By 2030, you could have a permanent base with power systems and life support running continuously. Mining operations start small, maybe a few tons of material per month initially, but you're proving out the extraction and processing techniques. Somewhere around 2032 or 2033, you might test a small-scale mass driver, launching just a few kilograms to validate the technology under real lunar conditions. If that works, and honestly, the physics says it should, you scale up. A full capacity system comes online maybe 2035, 2036. By that point, SpaceX wants to be sending cargo ships to Mars during every transfer window, which opens every 26 months. Suddenly, you have this dual supply chain developing. Specialized equipment and anything biological comes from Earth. Bulk materials and propellant come from the Moon. That's where the Mars connection becomes really clear to me. Every ton launched from the Moon toward Mars saves you from lifting that same ton out of Earth's gravity well. The energy savings are massive, probably 95% reduction in propellant requirements for the same delivered mass. Say you're building habitat modules on Mars, and you need structural steel. Launching steel from Earth means mining ore, refining it, forming it, then burning thousands of tons of rocket fuel to get it to Mars. From the Moon, you process regolith, extract the iron, manufacture steel using solar power, then launch it electromagnetically. Same steel arrives on Mars, but the total system cost is a fraction of the Earth launch scenario. This works for anything that doesn't need Earth's biosphere. Metals, ceramics, glass, basic chemicals, water, oxygen, all of it can be lunar-sourced and electromagnetically launched toward Mars. You're building a supply chain that completely bypasses the deepest gravity well in the inner solar system. What's fascinating to me is how this changes the architecture of Mars colonization. Instead of hauling everything from Earth, you bring manufacturing equipment and let the colony produce what it needs locally. But for specialized items Mars can't make yet, advanced electronics, certain medical equipment, specific alloy compositions, the Moon becomes your warehouse and distribution hub. Cargo packages launch from the Lunar Mass Driver, rendezvous with starships in lunar orbit, and continue on to Mars. Look, is this ambitious? Absolutely. There are probably a dozen major technical challenges that need solving. Automated mining in low gravity, precision trajectory calculations for cargo packages, Mars landing systems for bulk materials. But nothing here requires new physics. These are all engineering problems, and engineering problems get solved with enough iteration and resources. What gives me confidence watching SpaceX is how they actually operate. They don't announce grand plans and then spend a decade in development. They build hardware, test it, learn from what breaks, and iterate rapidly. Starship is flying right now. They're gathering data from every test, refining the design, proving out systems one by one. That methodical progression tells me lunar infrastructure is next on the roadmap, even if they're not advertising it yet. Once you have power generation and electromagnetic launch capability on the moon, the economics of Mars settlement shift fundamentally. You're not talking about a few heroic missions that cost hundreds of billions anymore. You're talking about sustainable logistics, continuous supply chains, the foundation for an actual off-world civilization. That's the difference mass driver technology represents. It's the piece that transforms Mars from an expensive science project into something economically viable for the long term. So, that's the real path to 1 million people on Mars. It's not bigger rockets from Earth, it's electromagnetic launch from the moon that turns an impossible fuel equation into something actually sustainable. SpaceX knows this. And while they're not advertising it yet, every Starship test brings us closer to that lunar infrastructure. If you found this breakdown valuable, hit that like button and subscribe to New Space Review. Drop a comment with your thoughts on mass driver technology. Do you think SpaceX can pull this off by 2035? I read every comment, and your insights help shape future videos. Thanks for watching, and I'll see you in the next one.